Welcome to Lecture 4. Today, we are looking at privacy and cyberspace, presented for the School of Computing at University Utara, Malaysia, by Dr. Ala Jabbar Al-Maliki. We begin with a definition. Privacy is the individual's right to govern their own personal information. In digital systems, that right manifests in three distinct vectors: information privacy, communication privacy, and location privacy. For computer scientists and software engineers, treating these vectors as simple legal compliance checklists often fails to account for the speed of technical development. This lecture frames privacy as a technical requirement that must be integrated into a system's core architecture. Designing these systems exposes a central paradox. There is an inverse relationship between computational convenience and data privacy. Every feature that pushes utility up almost always pushes privacy down. Think about free applications. They offer high utility at zero financial cost, but they extract background user telemetry in exchange for that access. This creates a system of asymmetric knowledge. Users frequently click Agree to terms of service without understanding the true scope and depth of the data extraction they are authorizing. This brings up the core ethical question of this lecture. Who actually owns the data generated in these environments? Is it the user who creates the footprint, or the platform that captures and processes it? Because modern network architectures inherently incentivize the extraction of maximum data, engineers have to make a conscious, active choice to build ethical safeguards into the platform. To map the overarching architecture that processes user information, we look at the personal data lifecycle's three major stages. Node 1 is gathering. This happens through passive collection, like registration forms, and active extraction, using tracking cookies and mobile sensors. A specific vulnerability here occurs when mobile apps request excessive hardware permissions, like a simple calculator app demanding access to your camera and GPS coordinates to function. Node 2 is exchanging. Data rarely sits static on a primary server. It is immediately routed outward into a secondary data broker ecosystem, shared with third-party services, advertisers, and sometimes governments. Tech giants like Google monitor and merge behavioral data across entirely different platforms, tying your search history directly to your location data and video views. The specific ethical failure in this cross-platform tracking model is a complete lack of transparency. The end user has no clear visibility into how these disparate datasets are being combined. Once your information is gathered and exchanged without rigid restrictions, you permanently lose control over your digital footprint. Note 3 is data mining. This is the algorithmic extraction of behavioral patterns from massive aggregated datasets to build unified profiles. Industry relies on this for three motives: delivering targeted advertising, running predictive analytics, and training AI decision-making models. The textbook example of a catastrophic ethical failure at this node is the Cambridge Analytica scandal. The company leveraged seemingly harmless interactions, like simple personality quizzes on Facebook, to harvest millions of data points without explicit user consent, building highly targeted psychological profiles. This level of profiling introduces severe downstream risks. It creates systems capable of algorithmic discrimination and completely strips away user anonymity. Individual raw data points might seem harmless on their own, but when they are aggregated and mined, they become a weaponized profile that removes the user's agency. This continuous extraction isn't limited to software interfaces on your phone. It extends directly into physical spaces through the architecture of the modern smart city. Public CCTV surveillance networks act as physical data gathering nodes. Unlike apps, citizens cannot simply uninstall a street camera or opt out of walking to work. We are currently observing a transition from passive video recording to active, real-time facial recognition networks. These systems process deep biological metrics, actively matching a physical human face to a permanent digital identity and a recorded location history. This presents a strict ethical paradox. On one side, mass surveillance architectures drastically optimize public security and law enforcement capabilities. On the other side, achieving that security requires the absolute obliteration of a citizen's location privacy and visual anonymity. In public smart spaces, the balance of power shifts entirely to the state. It forces a rigid societal choice between ultimate security and fundamental physical autonomy. If we look back at the complete personal data lifecycle map, we see severe vulnerabilities exposed at the gathering, exchanging, and mining stages. The engineering countermeasure to these vulnerabilities is the deployment of privacy-enhancing technologies, or PETs. The core architectural objective of a PET is to strictly minimize data exposure while preserving full system functionality. At the data entry and transit phases, engineers apply secure authentication protocols and end-to-end data encryption. At the network and database levels, the toolkit expands to include virtual private networks, strict dataset anonymization, and decentralized blockchain structures. Building ethical systems involves the active deployment of cryptographic and architectural defenses to protect the user from the system itself. Privacy is a core civil liberty constantly under pressure from both commercial platforms and state surveillance architectures. The responsibility to safeguard this right ultimately falls on the computer scientists who build the infrastructure of cyberspace. To test your application of these concepts, we turn to our final class discussion prompt. Should governments use facial recognition in public places for security? As you approach this, you must explicitly identify and weigh the technical benefits against the privacy risks of the technology. Apply the definitions we covered today to determine who rightfully owns public movement data. Then, provide a robust, architecturally sound justification for your final stance on the dilemma. Remember, the code you choose to write today dictates the civil liberties of millions tomorrow.